Hello. In this tutorial, we're going to perform a general static analysis on a truss structure using Abacus Standard. The truss is displayed on the monitor behind me. The truss structure is fixed at one end with pin joints, which means it cannot move or translate in the X or Y direction. However, it is free to rotate about the Z-axis. Three concentrated forces of 3,000, 5,000, and 6,000 newtons are applied at three nodes of the truss. We are going to use the dimensions from this schematic. We will be using SI units, where length is in meters. The radius of the truss members is 1 centimeter, or 0.01 meters. The truss is made of steel with a density of 7.8 grams per centimeter cube, a Young's modulus of 200 gigapascals, and a Poisson's ratio of 0.3. The truss in this example is a two-dimensional truss, so we're going to be working in a 2D plane. This means we're not going to create a 3D model of the truss the way we created a 3D model of the barbell stand. Instead, the truss members are going to be modeled using line segments. Then we're going to create sections, truss sections, and assign these to the truss members. And when we mesh the model, we're going to use truss elements and apply them to the entire truss structure. In Abacus, truss elements carry only axial loads, and they deform only by axial stretching. Basically, truss elements are one-dimensional bars or rods. Since truss structures, at least theoretically, are designed to carry purely axial loads, that is tensile and compressive loads, and do not undergo bending, this makes Abacus's truss element the ideal element for truss analysis. The joints in our truss will be pin joints, which means they can only transfer forces, but not moments, since pin joints allow rotation. However, we will not specifically be telling Abacus that the joints are pin joints, because truss elements in Abacus are expected to be pin jointed at their nodes. Now that we've got it all planned out, let's get started. We're going to start by renaming the model. Right-click on Model 1 in the Models tree and choose Rename. Type in Truss Structure and click OK. Next, we're going to create the part. Double-click the Parts item. You see the Create Part window. Let's name our part Truss. Since it's going to be a 2D truss, we're going to set the modeling space to 2D planar. We can set the type to deformable, since the truss structure will be deforming under loads. And we'll set the base feature to wire, so we can model the elements of the truss by using wire features. We can set the approximate size to about 10 meters, since this will help with sketching. Then click on Continue. You enter the sketcher mode. We're going to sketch the truss by using the Create Lines Connected tool. You can draw the elements of the truss by moving your mouse around the screen and clicking. Every time you click, you create a node. In this way, you can draw out the entire truss, and when you want to exit out the Create Lines Connected tool, right-click and choose Cancel Procedure. Some of the segments of the sketch span more than one truss element. Therefore, we need to split them up. We can do this using the Split tool. You might find the Split tool hidden behind the Auto Trim tool. To reveal the Split tool, press down on the Auto Trim tool with your mouse. This will reveal the rest of the toolbar. The Split tool is the last tool on the toolbar. At the bottom of the Sketcher window, you can see Abacus prompting you to select the curve that needs to be split. So select the line segment that you want to split, and then select another line segment that intersects with it. The split will be created where these two lines intersect. Repeat the procedure until all the line segments are independent truss elements. We shall now use the Add Constraints tool To specify which of the elements of the truss are of the same length, click on the Add Constraints tool. You see the Add Constraints window with a number of options. Choose Equal Length. Below the Sketcher window, Abaqus prompts you to select the lines for the equal length constraint. You can select multiple line segments by holding down the Shift key and clicking on them. Then click on Done. Repeat the procedure for the other set of equal length segments. We shall now dimension the truss using the Add Dimension tool. Click on each truss segment that you wish to dimension and type in the length in the prompt at the bottom of the Sketcher window. Then hit the Enter key on your keyboard. All the members of our truss have one of two lengths. Since we've already told Abaqus which of the segments share the same length, we only need to enter the dimensions twice. Click the red X below the Sketcher to exit the dimensioning tool. Then click on Done to exit the Sketcher. You can now see the truss displayed in the viewport. Next, we're going to create the material. Double-click on the Materials item. In the Edit Material window, set the name of the material to AISI 1005 Steel. The first material behavior we're going to specify is density. Under the General tab, click on Density. The density of our steel material is 7.872 grams per cubic centimeter. However, we typed in the length of the truss segments in meters, and remember, in Abaqus you need to keep your units consistent. Therefore, we're going to set our density to 7,872 kilograms per meter cubed. Next, we're going to set the elastic properties of the material. In the Mechanical tab, choose Elasticity, and from that choose Elastic. The Young's modulus of steel is 200 gigapascals. But once again, remember we need to keep our units consistent. Therefore, we need to write the Young's modulus in pascals. We express this as 200 times 10 to the 9th, or 200 E9. The Poisson's ratio is 0.29. Click OK to close the Edit Material window. You see that our newly created material has been added to the Materials item. Next, we need to create a section. Double-click on the Sections item. In the Create Section window, name the section Truss Section. Set the category to Beam and choose Truss from the type. This tells Abaqus that we're creating a truss structure. Click the Continue button. In the Edit Section window, make sure that the material is set to steel. For the cross-sectional area, type in 3.14 E-4. We get this number because the radius of each truss member is 1 centimeter, or 0.01 meters, and you multiply, you square that and multiply it by pi to get the area, and that gives you 0.000314116. Then click the OK button. We can now assign this section to the truss. Expand out the parts container and expand out the part called truss. Double-click on Section Assignments. Abaqus prompts you to select the regions to be assigned a section. Using your mouse, select the entire truss structure. You see it light up in red. Then click the Done button. In the Edit Section Assignment window, ensure that the section is set to the section you've just created, which is the truss section. Of course, you don't really have any other options anyway. Then click on OK. I'm going to collapse the parts container so the rest of the tree is visible. Next, we're going to create the assembly. Expand out the assembly container and double-click on Instances. Notice that you are now in the assembly module. In the Create Instance window, set the instance type to dependent with mesh on the part. When we later create the mesh, we're going to create it on the part itself, as opposed to creating it on an instance in the assembly. Click the OK button. You see that truss has been added to the instances container. Now let's define the steps in the simulation. If you expand out the steps container, you notice that Abacus has already put the initial step in place. Double-click the steps item and you get the Create Step window. We're going to name our step Loading Step. It has by default been inserted after the initial step. We set the procedure type to a static general analysis and click the Continue button. We can type in a description in the Edit Step window and then click the OK button. Next, we create the field output requests. In the field output requests container, Abacus has gone ahead and created a field output called foutput1. Let's rename it by right-clicking on it and choosing Rename. We'll name it Selected Field Outputs. In the Edit Field Output Request window, by default, the domain is set to the whole model, and the frequency is set to every n increments where n equals 1. We're going to leave these set at the defaults. For the output variables, we're going to disable strains and contact, and leave the rest of them at the default values. We are not going to create any history output requests in this simulation. Our next step is to create the loads. In the Create Load window, set the name of the load to Force 1. Ensure that the load will be applied during the loading step. For the category, choose Mechanical, and for the type, choose Concentrated Force. Then click the Continue button. Abacus prompts you to select the points for the load. Select the node inside the viewport. Click the Done button. In the Edit Load window, we're going to set CF2 to -3000. This is because we want a force in the negative y direction of 3000 newtons. We have no forces in the x direction, so we leave CF1 blank. Click on OK. Our new force, Force 1, has been added to the loads container. Repeat the process for the next two forces in the negative y direction of 5000 and 6000 newtons respectively. Next, we create the boundary conditions. Double-click the boundary conditions item. Our first boundary condition is to pin one end of the truss. In the Create Boundary Condition window, set the name to Pin. We set the step to the initial step. The category is Mechanical, and the type is Displacement Rotation. Click the Continue button. Abacus prompts you to select the regions for the boundary condition. By holding down the Shift key, you can click both the nodes on the truss structure that you would like to pin. Then click Done. In the Edit Boundary Condition window, we're going to check off U1 and U2. This is to prevent translation in the X and Y directions. However, we're not going to check off U3 because we want to allow rotation in the XY plane, or rotation along the Z-axis. This gives us a pin joint. Click on OK. You notice that the constraints are displayed in the viewport, and that our new boundary condition has been added to the boundary conditions container. Our next step is to mesh the truss. When we instanced the truss inside the assembly, we specified that the instance would be dependent, which meant that the mesh will be on the part. So expand out the truss part in the parts container and double-click on Mesh. You are now in the Mesh module. Our first task is to set the element type. You do that from the Mesh menu by selecting Element Type. Abacus prompts you to select the regions to be assigned element types. Select the entire truss using your mouse and click the Done button. We set our element type to 2-node linear 2D truss elements. Click the Done button again. Now we're going to seed the edges of the truss. From the Seed menu, select Edge by Number. Abacus prompts you to select the regions to be assigned local seeds. Select the entire truss once again and click the Done button. We would like to have 4 elements for each segment of the truss, so type in 4 and hit the Enter key on your keyboard. We can now mesh the part by choosing Part from the Mesh menu. When Abacus prompts you to mesh the part, click the Yes button. The truss changes color in the viewport, indicating that it's been successfully meshed. And you see the message, 10 elements have been generated on the part at the bottom of your screen. Now we can create the job. In the Analysis tree, double-click on Jobs. In the Create Job window, set the name to Truss Analysis Job. Make sure that the source is set to the model and that truss structure is selected. Click Continue. In the Edit Job window, you can add a description of the job. Make sure the job type is set to Full Analysis and click on OK. Truss Analysis Job has been added to the Jobs container. To run it, you can right-click on it and choose Submit. If you've already run the simulation once before, Abacus might warn you that the job file already exists and it's going to get overwritten. I'm going to click on OK. Abacus runs the job and completes it successfully, as indicated by the word completed in parentheses. In order to view the results, you can right-click on it and choose Results. You are now in the Visualization module. You can view deformed and undeformed shapes of the truss structure by clicking on the View Deformed Plot and View Undeformed Plot tools. If you'd like to have both deformed and undeformed plots overlaid over one another, use the Allow Multiple Plot States tool. It's possible you might later need to read the output file and would like to know what the node labels are. To display them, click on the Common Plot Options tool. In the Common Plot Options window, go to the Labels tab. You can check off Show Node Labels and click OK. The node labels are now displayed in the viewport. Next, we would like to plot the displacement as a color contour. From the Result menu, choose Field Output. Choose Spatial Displacement at Nodes and Magnitude. This will display the magnitude of the displacements in the color contour. In order to display it, we set the plot state to Contour and click OK. Now let's try displaying the U1 component of the displacements, which is the component in the X direction. From the Result menu, once again choose Field Output. This time, instead of selecting Magnitude as the invariant, we're going to select U1 as the component and click OK. And now you see the X component of your displacements have been plotted in the viewport.